Hey, can you hear me?
Yeah, okay. But I don't see your screen.
Yeah, sorry. There must be something. I'm on a wired connection here at the university, but there must be something going on right now because a lot of package drops. Um,
Yeah,
can you see
okay.
it now?
For a while we did. Okay, we can see now.
Okay, and you can hear me okay?
Yeah, that's good now. Okay, I think we can start. We have 35 people connected. So today we will discuss some of the activities of the work package 1, which is advanced mathematical models of the instrumental components. And we will focus mainly on alpha plate for this series of talks. The first one will be by Jon Gudmundsson, and we'll talk about probing frequency-dependent alpha plate systematics for CMB experiment with full sky beam convolution simulation. Very interesting topic. And go ahead. You have 25 minutes, so something like that.
Okay, sounds good. Yeah, my name is Jon Gudmundsson, and I'm at Stockholm University. So this is the title of the talk, and it's also the title of a paper that I'll introduce on the next slide. I want to say, however, that this is work that's done in collaboration with Adri Daufenhoeden, who was a PhD student at Stockholm University, now a postdoc at Princeton University, Alexander Adler and Nadia Dachlithra, who are PhD students here at Stockholm University, and Matteo Billi, who is a PhD student at the University of Bologna. I also want to draw your attention to sort of a discussion in WP4, which will happen next week, where Marta Monelli and Alexander Adler will talk about a related topic. Okay, so what you see here in the background is an image of the spider flight cryostats in Texas during a calibration run. And what you see here are actually halfway plates. These are 30 centimeter diameter sapphire plates that were placed in front of the primary lenses on spider. And you can actually see 5 out of 6 mounted in that image. Now, the paper that I'm going to tell you about today is this one here, which was published in Monras February this year. And yeah, like it says, it's sort of, we're looking at frequency-dependent halfway plate systematics for CMB experiments. Now, this is the second paper in a series of papers describing an algorithm that we call BeamConf. Shown here, the first paper came out in 2018. And this is an open source beam convolution algorithm. And in this particular paper, once we introduce sort of a new analysis framework and a new sort of extension to this algorithm, we use a fiducial satellite experiment, or create a fiducial satellite experiment that is composed of a 2-lens refractor system with an achromatic halfway plate, and we scan sky models and generate time streams, maps, and power spectra to understand how non-idealities in the halfway plate and our optics impact our ability to understand degree scale polarization. I guess I should say, please don't hesitate to interrupt me unless Francesco feels otherwise. I'm happy to sort of
I think we should keep it informal. So
yeah, absolutely. Yes, absolutely. I think that's the right way to go. So if you have questions, please interrupt. One of the arguments that we maintain in our group is that this functionality should be incorporated into future simulation infrastructure, such as TOAST and Lightbird simulation framework, for example. So I guess that's going to be a matter of conversation for WP4. So there's sort of an interplay between these two work packages for sure. For the people that are new to halfway plates, and I guess since I'm the first in a line of talks about halfway plates, I can spend a minute on this slide. So the reason we use these on CMB experiments is because, well, there are 2 reasons really. They improve cross-linking, and they allow us to modulate our polarized signal relative to the unpolarized light, which then allows us to sort of suppress the impact of low frequency thermal noise variations in our system. And the most common example that is given of a half-wave plate is basically a piece of birefringent sapphire crystal, where the speed of light depends on the polarization of the incoming light. And so if you chop your sapphire plate to a certain thickness, two plane waves coming in that are perpendicular polarizations, they will become, they can be in phase as they enter the plate, but then once they emerge on the other side, they'll be shifted by half a wave, and that's a half-wave plate. So this is a rendering of the spider optics, which is sort of, well, quite similar to the proposed baseline Liebert refractor designs, two lenses, a secondary lens and a primary lens. And the half-wave plate in our case is placed just in front of the primary lens over here. Okay, so so this slide here is just to emphasize the point that once you spin your half-wave plate, you're actually modulating the polarization at 2 times or actually 4 times the spin frequency of the half-wave plate. And so if you have a 1/f thermal noise component, well, which is essentially unpolarized, which is swamping the polarized signal that you're trying to study, if you spin your half-wave plate, you'll be modulating that signal at 4 times the spin frequency. And using proper analysis, you'll be able to move that, demodulate that signal and get the time stream that represents the polarized signal on the sky. And I think this is a beautiful video showing the next generation polarization modulators that we're developing as a community, using superconducting magnetically levitating bearings. I guess this video I stole from a talk that Masashi Hasumi gave last year, and lots of publications on this work linked here on this slide. Okay, so if we continue, so in these 2 papers on the BeamConf algorithm, we work with this fiducial satellite experiment that is beautifully rendered here on this slide. So 2-lens silicon refractor design. And imagine now that this telescope is scanning the sky, observing the cosmic microwave background, generating signal time streams. Now those time streams, as you know, represent a convolution between the spatial response of a telescope, the beam, and the power on the sky. Right, so this is the signal. This is sort of a rough expression for what the signal in our time stream looks like. Yes, and at every point in time, we are in fact doing a convolution. But as you know, a convolution is a relatively costly operation, and so in order to simplify and make this computationally tractable for us, we use the trick that convolution in real space is a multiplication in Fourier space, right? So, what that amounts to some extent, is the following equation. So our time-ordered data is a sum over spherical harmonic coefficients, where the 3 factors here are the beam response in the multiple domain, the spherical harmonic transform of the beam, the ALMs of the sky, and the spherical harmonic functions, right? And so for azimuthally symmetric beam, this data model is really simple to compute because we don't care about the scan strategy. Well, we don't care about the orientation of our beam. So these beams are azimuthally symmetric. Now, when the beam becomes elliptical or has some aspect to it that breaks this azimuthal symmetry, things get a little bit more technical. And so this is the expression that roughly captures what's going on then. So in this scenario, we actually have to keep track of the non-zero m coefficients of the beam transfer function, as well as the orientation of our telescope with respect to the scan strategy. So this is the ellipse that describes the beam in this particular case. And so all of this is done in this algorithm called BeamConf, which was first published in 2018 in a Monroe's paper, where we, among other things, published or showed these diagrams here. And I guess the thing to emphasize is that we can take for these simulations arbitrarily shaped beams. so Stokes IQ, U, and V beam shapes, arbitrary pointing strategies or scan strategies, and we can generate signal time streams that can then be pushed into maps. So the core of the algorithm is first described in a paper by Gary Persaud and Martin Reinecke in 2010. And I believe this is also based on work that done by Chris Gorski and Benjamin Wendelt at the turn of this century, early 2000s. So that's, but this, in some sense, was the first time this code was made publicly available. And in the case of Beamcom, this is 100% in Python. So it's relatively easy to digest. So I haven't started talking much about half-wave plate non-idealities and how they relate to Beamconf, but before I do that, I want to show this slide here. So imagine you have a satellite scanning an input map, which is consistent with Lambda CDM. These are Stokes IQ and U realizations of the microwave sky. So this is the CMB. In 1,000 samples, this satellite goes from the North Pole down to slightly below the equator, right? And this is a 19 arc-minute beam, roughly speaking, in terms of size. And so what's being shown in these panels is a Gaussian approximation of this beam. And the fact that this goes from -200 to +200 is just representative of the fact that the primary anisotropes have an RMS of roughly 200 or 300 microkelvin. Meanwhile, the bottom panel here is representative of a hypothesized primordial beam mode signal that might be there on the sky. This is the thing that we're looking for, right? Now, and I think that this realization is consistent with the current 95% confidence limit of a intensity to scalar ratio of about 0.036. So in our time stream, we will be having a 50 nanokelvin signal from a primordial gravitation wave background at most. Okay, so now let's increase the complexity of our beam model. Instead of a Gaussian beam, let's have an elliptical Gaussian beam. The time stream looks like this. You can't really see the difference until you difference the time streams, and then you're left with something that is roughly 500 nanokelvin RMS. So it's a factor of 10 times greater than the signal from a primordial gravitation wave background. This is what I refer to as a PO beam, which is essentially stands for physical optics. So this is sort of a more complex model of what the beam for this fiducial two-lens system looks like. So this is based on relatively advanced optical simulations. Okay, so in that case, the residual is a factor of 10 times greater. So now the difference between these two beam models is 5 microkelvin. If you inject side lobes to your model, instead of truncating your beam at 3 degrees, you let it go all the way to 30 degrees, things get even worse, right? The difference between a Gaussian beam model and the PO beam with a side lobe is now roughly 10 microkelvin in the signal time stream. Okay, so the whole point really is just to, I guess, scare us. The optical non-idealities that we're not accounting for or might not be accounting for in our analysis are much larger than the signal that we're looking for. Okay, so once this first paper was out and we were happy with it, we decided that we wanted to add the functionality of having a halfway plate that is modulating the spatial response and the polarization response of our instrument. And this was spurred by the arrival of Matteo Billi, who came to Stockholm University for a 3-month project. Adri and I decided that it would make sense to just add this feature, the ability to have a halfway plate. We thought that that was a pretty well-defined 3-month project. In the end, it turned out that adding this halfway plate and figuring out all the details of the sort of the analytics was something that took the 5 of us, Alexander and Nadia, added to the effort more than a year to work out. Okay, so now what we're doing is we can take arbitrary input models of the sky with CMB and galactic foregrounds, and we can have Stokes IQ, U, and even Stokes V models of the beam, and we modulate that with a half-wave plate. One way to think about the data model that we're dealing with is the following. So you can think about it as a sort of matrix multiplication, where you have something that relates to the sky model, something that relates to the scan strategy of your instrument, and then something that relates to your instrument model, right? So this is the color scale here refers to how how the different factors are related to these three concepts. Now, what we ended up with in this paper, once we'd figured out the analytics, is sort of a more complex expression that you can see here. And this will actually take me some time to go through just to make sure that I capture everything that's important. So this I here refers to the unpolarized part of the beam, Stokes I beam. This is a Stokes V beam. This is the Stokes P beam. Well, not Stokes. This is essentially the pseudoscalar representation of the beam, taking both Q and U into a new component. What we see when we look at this expression is that the stuff that has to do with the unpolarized part of the beam can actually be broken up into several terms, some of which are stationary or unmodulated by the half-wave plate, and some of which are actually modulated by 2 times the modulation frequency of the half-wave plate. The same can be said about Stokes V, because it's also a scalar field on the sky. So you get essentially the same behavior. But things get a little bit more complicated for the polarized part of the sky and the beams. So now you have terms that have a 2 alpha dependence, a 4 alpha dependence, and also a term that is not modulated by the half-wave plate. One thing that I haven't pointed out in these 3 slides is the fact that what do all these terms actually mean? So this uppercase I and then comma II actually means that what we're doing is we're taking the Stokes IB model and we're multiplying it with the Mueller matrix coefficient II. And this is the Stokes V B model, and we're multiplying it with the Mueller matrix coefficient, which corresponds to the cross term between Stokes V and Stokes I. And if you want to get the technical details, I just referred you to the paper that I mentioned on slide 2. Okay. Are there any questions at this point?
Let's see questions. So go ahead.
No questions. Okay. So in order to arrive at that analytical expression that I just showed, we needed to make an approximation. So this telescope, the system that we have, is composed of 2 lenses and a half-wave plate that is placed right in front of the lens. And when we describe Mueller matrices that are used to describe the impact that a half-wave plate would have on plane waves, they're not necessarily ideal for this particular situation, because if you think about things in the time reverse sense, there's electromagnetic fields that are going from the focal plane through the lenses and outwards. But these, although these are relatively well collimated beams by the time they hit the half-wave plate, they are not well described by plane waves. So in order to arrive at that expression, we needed to utilize or rely on the plane wave Mueller matrix description. Okay. So, in other words, the approximation that we did in all this is that the physical beam that is defined by the 2 lenses in our telescope is treated as if it's a plane wave that is then hitting the half-wave plate and then propagating out to the sky. In fact, this is only valid if the radiation field between the half-wave plate and the beam-forming elements is principal to the ray, is parallel to the principal ray of the optics. So we allow ourselves to break up this instrument Stokes vector into the Stokes vector that represents the beam and the Mueller matrix that represents the halfway plate. Okay, and it actually is a big question whether or not we can account for near-field effects or near-field interactions between the lenses and the halfway plate in a more advanced framework. I think that's well beyond the scope of this work. Okay, so a halfway plate Mueller matrix as a function of frequency might look something like this. So in the ideal case, you only have non-zero coefficients along the diagonal, 1, 1, minus 1, and minus 1. For non-ideal halfway plates, you do in fact have off-diagonal terms, right? And in this paper, we studied the impact of 3 different types of halfway plates. So you can have a simple single birefringent layer, so what we refer to as BR1 in our paper. You can have a 3-layer halfway plate or 5-layer. You can have arbitrary number of layers, and I think we might actually talk about that later today. The reason you would actually have multiple layers in your halfway plate is because it allows you to have a broadband frequency coverage. So one thing that you'll notice is that if you look at the Stokes UU or Mueller matrix UU coefficient of the single layer halfway plate, it actually is nowhere close to being at the -1 ideal scenario. It actually is varying quite significantly across the frequency, right? And by the way, in this paper, we're studying a telescope that has 2 frequency bands, one that is centered at 95 gigahertz and one that is centered at 150 gigahertz. And so in that case, you want to have a halfway plate that has a broadband frequency performance. So you can achieve that by having multiple so-called achromatic halfway plates. So a stacked halfway plate configuration with 5 different plates rotated one with respect to one another actually gets you pretty far in terms of being close to the ideal scenario. Okay, and so in this paper, what we did is we scanned models of the sky with these halfway plate models, and we actually sampled, we ran simulations at sub-frequencies within these 2 frequency bands to understand how the fact that we have non-idealities in these Mueller matrix coefficients impacted our final analysis. And I have these transitions that I'm showing now that tell us a little bit about how, as you increase the number of layers in your halfway plate, you reduce the overall sensitivity. You get fewer photons that propagate through your system, but you in return you get better polarization modulation efficiency. So the blue line here is essentially flat or quite flat across the entire frequency range, both in QQ and in UU. Okay. So how much time do I have left? I have 2 minutes. So one thing that you can do once you've implemented this algorithm is that you can scan the sky for 2 hours. And this is just a lambda CDM sky realization with ideal halfway plates and with non-ideal halfway plates. And the thing that I want to draw your attention to is the fact that the polarized signal, if you scan a realization of the sky that only has polarization, you actually, with a non-ideal halfway plate, you will get, when you look at the PSD of the signal time stream, you will get a small peak here at 2 times the modulation frequency of the halfway plate. So this is a plot that we made once we were happy with the algorithm to verify that in fact, it was generating what we expected. We saw a systematic effect popping up in the PSD of our time stream. Okay, so yeah, so the next thing that we did was essentially we know that there's galactic foregrounds that are much brighter than the signal that we're looking for, and we used different realizations for different models within the PySM simulation framework of galactic foregrounds. And I tried to understand how, by increasing the complexity of the galactic foregrounds, we would actually change the residuals that we're seeing in our angular power spectrum. So the simulations that we ran, we modeled 50 dichroic detectors with a 30 gigahertz frequency band centered at 95, 150. And so we sampled at 7 frequency intervals within those bands. So in the case of 95 gigahertz, we go from 80 to 110 gigahertz in steps of 5 gigahertz. And then, yeah, we changed the half-wave plate models. We had 1 layer, 3 layer, 5 layer, and we changed the PySM input models to our simulations. And I don't have time to go over many of the details that we found, but essentially the takeaway from
we have some margin, so I mean, take your time if you.
Okay, well, basically what we find, and this is sort of what we expected, is that in order to properly clean our data from galactic foregrounds, we need to have accurate knowledge of the half-wave plate Mueller matrix. And depending on the complexity of the foreground model, the residual that you get in the angular power spectra or in the map domain can change. So one thing that we found, and this was largely known, is the fact that a 3-layer achromatic half-wave plate induces significant bias in our maps, because essentially there's a significant frequency dependent in the phase shifts, depending on whether you're looking at the CMB or dust. So if you scan the sky and assume that you're looking at the CMB and assume that the spectral energy distribution of the CMB in your analysis, then you will get, when in fact you actually are looking at galactic foregrounds which have a different SED, you will get significant residuals that are comparable to an R of 0.003. So that was one finding that came out. Another thing was that we now saw residuals in our angular power spectra that are related to the interplay between the far side lobes of our optical elements or of our optical system and the Mueller matrix and the complexity of the half-wave plate. So in some sense, you always worry about beam side lobes when we talk about systematics for CMB experiments. But in this plot and in this analysis, we show that there are effects that combine beam side lobes with half-wave plate non-idealities. And I think that was quite interesting. So I was actually trying to write the conclusions a few minutes ago before this talk, but I didn't have time to finish the conclusions. But I think that really the takeaway is that we have this new pipeline that is really powerful. It folds half-wave plate non-idealities with beam non-idealities. There's a lot of things that we can learn that we haven't really done yet, but we have now the tools to do that. I think to some extent, this quote from a recent Beyond Planck publication really captures the take-home message, right? And I guess that's also one of the things that we'll be keeping in mind in this CMB-INFLATE collaboration, which is the fact that we need to keep track of our instrument model and the complexity of our instrument as we're doing cosmological analysis and component separation. So I'll stop there and take questions.
Thank you very much, Sean. Very interesting. Is there any question?
I have one.
Mm-hmm. Okay.
Thanks a lot for this presentation. Actually, it was really nice and really in the spirit of what we want to develop. So this is great. I was wondering, when you showed the different terms of the beams, which interplay with the different parameters of the Mueller matrix coefficients.
Yeah.
So I guess you tested that with models, right? That you made probably for the different terms. And what did you use for those beam components?
Yeah. So I didn't talk about that. I guess in this talk could have also been 25 minutes focusing on how do you estimate half-wave plate millimeters and how do you estimate these beam models. What I can say is that I don't know if that is actually answering your question, but I'll try, and then you can correct me. So the beam models are based on grasp physical optic simulations, which is a term that I think you've heard about before. So we have the two-lens silicon refractor, and we run physical optic simulations for each detector individually, and we get Stokes IQ U and V beams for that detector. And then the half-wave plane Mueller matrix elements are based on, and I say that here, although I didn't mention it in the talk, there's an open source Mueller matrix algorithm that basically you give it arbitrary stacks of birefringent crystals with where you input the crystal axes, the orientation of the crystal, and the index of refraction for the fast and slow axis, and the code will give you the Mueller matrix as a function of frequency and as a function of incidence angle of the plane wave. So we take all that into account when we generate, for example, this plot, and in all of our analysis, we use this code that was developed by Tom Hilleman.
Okay.
So does that answer your question?
Yeah, sure. And okay. One, Francesco, can I ask another one?
Let's see. We have just scan first. Let's go in.
Okay, I'll be quick. Thanks, John, for the great talk. In one of your last slides, you mentioned the phase angle correction.
Yes.
Which depends on the ACDs. I understand of the sky signals. Yeah, this one.
Yeah.
And I just wanted to point out, maybe we should talk offline. We did a similar exercise with Clara Vergès and collaborators for the Silence Observatory, right?
Yes.
And yeah. And so that's
I reference you here.
Okay, cool. I think it's a good motivation to see that the galactic cleaning that will be discussed in another work package has to be definitely performed jointly with the estimation, this phase angle correction of the alpha plate, because the ACD is one of the unknowns of the problem. So we have to correct for everything, characterize everything at the same time. Right?
Yeah, no, totally agree.
Thanks. I have also a very quick question. So when you make your frequency dependent simulation, do you use frequency dependent beams also, or not? Is there an impact?
Yeah. So what we did, and this was just to in this paper, no. So we used a physical optics beam model at the center band frequency, but that's not because we couldn't do the other thing. It's trivial for us to generate, at these sub-frequency components and run it that way. The reason we chose to only use a single, like a frequency independent beam model, we used a beam model for the 95 and a different one for 150, right? But not across the band. The reason we did that is because we wanted to understand primarily in this publication the impact of these non-idealities and not the beam effects. But it is also, when we calculate these residual plots in this publication, we do correct for everything that has to do with the fact that the beam is actually not a Gaussian. It's a physical optics beam with complex structure. We actually, in our analysis, the way we calculate the residual maps, which we then feed into calculating the angular power spectra, we actually account for the beam shape as well as is possible.
Okay.
Yeah.
Thank you. Guillaume, quick one.
Yeah. But I guess that's something we can discuss after the talks. But how do you see the development starting from this for within the CMB-INFLATE framework? But this is
maybe we keep it for the end.
Yeah.
Okay. We'll keep that for that. Yeah. Okay. I'll stop.
Thank you very much, Jan. Very interesting discussion. So we now have Ryota Takaku, University of Tokyo. Are you? Yeah.
Okay.
Yeah. Hello. Can you try sharing your screen?
Hey.
Yeah, we see you. We see your Mac background. Okay. Good.
So you can see the title and also, okay. So thank you for the giving me such a time. So I'm Ryota, the PhD student from the University of Tokyo, and basically I'm I'm working with at the Kaburi IPMU in Japan. So my study is related to the development of broadband chromatic half-wave plate and with the anti-reflective subwavelength structures. So I will talk about that. So I think can be the kind of reminder that. So I will start from the short introduction. Maybe you know well. So to measure the primordial B mode large angular scale, it is expected to play a role to cover some of the van der Waals noise and the critical the systematic effects. But so in order to probe the B mode precisely, for example, the delta R is less than 10 to minus 3, which is the goal of the light bulb. So it is essential to understand how half-wave plate behaves in the polarimeters and the instrument to mitigate the systematic effects. But so the half-wave plate itself has also the source of the systematic effects. So in this talk, we will review the status of the development and modeling of the sapphire-based half-wave plate. So for the future satellite beam, such as the LightBird project. So since the half-wave plate is the one of the source of the systematic effects, we need to care about the half-wave plate itself. So there are many items to study the half-wave plate parameters. But so when we list the major the items, so for example, we need to high transmittance and the modulation efficiency to maximize the throughput and thus the increase the signal to noise ratio. And so we also need to rotate half-wave plate to modulate the signal, but so the uncertainty in the half-wave plate angle reconstruction leads to the E to B mixing. So we also need to minimize this uncertainty. So and there are the reports about the instrumental polarization, which is the conversion from the unpolarized to polarized light. So the instrumental polarization introduces the test detector nonlinearity effect. So we also need to minimize the request from I to P. So but there is a limited time limited. So in this time we'll present the half-wave plate modeling to achieve the broadband transmittance and modulation efficiency. So and also its experimental validation. And before going to the modeling of half-wave plate, maybe it is useful to know where our study is using the simple entire analysis flowchart. So there are two parts. The one is to develop and validate the instruments, and the other one is to propagate the instrumental parameters to the tensor to scalar ratio. And we need to iterate the development with the cycling and this flow to improve the systematic effect. So, and in this talk, we will focus on the instrumental for development. So we designed the half-wave plate model and simulate the optical performance using the proper the calculation methods and validate the model by the publication and measurement. And then we can use the value of half-wave plate, for example, the mirror matrix of half-wave plate for the TOD data. And so now our development is now focusing on the instrumental development. And so in particular, the modeling of half-wave plate, it consists of the multiple layer half-wave plate and the reflection coding for the broadband modulation. So, and for the modeling multiple layer half-wave plate, we also propose the design with the frequency independent interface, which can delete the extra term of the modulated signal, and so that it can reduce the systematic effects. And for the modeling of the anti-reflection coating, we also propose the subwavelength structures, SWS, equipped on the both surfaces of the half-wave plates. So, and the coupling with the number 1 and 2, we can calculate the mirror matrix of the achromatic half-wave plate with subwavelength structures, and it includes the modulation efficiency and transmittance and instrumental polarization and the other components. And the mirror matrix is here. So actually, we also need to care about the rotation angle, rho, which rotates the mirror matrix of this half-wave plate, but I don't introduce the detail in this time. So today I will focus on the modeling number 1 and number 2. So in the number 1, for the designing the chromatic half-wave plate, we can optimize using the analytical approach, and it leads us to model the half-wave plate very, very easily. And so basically the stacking half-wave plates for the broadband modulation, this is proposed by the Pancharatnam, and we need to optimize the parameter of the half-wave plates. So in particular, the relative, the specific optical angles. And so assuming the no effect of reflection on any surface of the wave plates, we can calculate the mirror matrix of the multiplayer half-wave plate by integrating the mirror matrix of each half-wave plate and rotating matrix. So the mirror matrix of each plate can be described using only the retardance of half-wave plate. So it can be easy calculation. And once we get the mirror matrix of the multiplayer half-wave plate, then we can calculate the modulation efficiency. So with respect to the measurement, the polarization detection, we can calculate the polarization angle, using the detector only have the sensitivity on the one direction as a function of the rotational angle. Then the amplitude of the modulated signal can be the modulation efficiency, and also there is the phase of the modulated signal at each frequency. So this is the only other one frequency, the rotational angle, rotational signal. So and then we optimize the model of the half-wave plate using assuming a few models. So there's 2 representative models. One is a symmetric design, which can be the typical type, and so the anti-symmetric design, which is we proposed in the paper given by the Kunimoto, Komatsu et al. So is an anti-symmetric model. It has the phase with the completely independent on the frequency. So you can see the phase as a function of frequency. So this line is the overlapping the anti-symmetric design. So, and the both symmetric and anti-symmetric design had the broadband modulation efficiency. So, but I don't put the detailed optical angles, so you can find the detail in this paper. So the conclusion here is that the analytical approach is very useful to optimize the design. So we came up with the design which the refractive effective optic axis is completely frequency independent. And so, but so I have to note that this is the optimization without any reflection effect. So we need another approach for the realistic modeling. So, and we should care about the reflection of the half-wave plate. So in order to reduce the reflection, we also need the broadband anti-reflection coating, and we propose applying the subwavelength structures on the surface of half-wave plates. So, and actually we have developed the technique of laser ablation to make subwavelength structures on hard materials such as sapphire, silicon, and alumina. So you can find the development as shown in these papers given by our teams. So, and this is my paper. So this is my main study. And so in the subwavelength structures, we can calculate this effect using the very rough approximation named the effective medium theory. So we can assume that the SWS part, the uniform substrate, and the effective refractive index that increases along the depths and structure height. But so it is so the rough approximation. So we need the more accurate calculation. So we use the numerical approach using the rigorous coupled wave analysis named RCWA. So this method is to solve the Maxwell equation in the Fourier space of the permittivity distribution with the periodic boundary condition. So this method calculates the optical performance for the structured surface, and which repeating the infinity in X and Y. So this method is useful for the calculation of this model. So, and this is also our development not directly related to the CMB polarization measurement. But so this is the good example of the RCWA calculation is very accurate. So we designed and fabricated the structures on both surfaces of the alumina over the diameter of 300 millimeter. And this structure is fabricated by using the ultra short pulse laser ablation. And you can also find the detail in my paper. And so this aluminum filter is targeted, it's targeting the frequency band between the 75 and 105 gigahertz. And this is used for the IR filter. And so we measure the transmittance here and of the fabricated filter. So, and we achieved the 98% transmittance averaged in band. And I want to emphasize that the measurement data is here. The measurement is consistent with the RCWA calculations. This calculation is based on the measured shape. So this implies that the RCWA calculation can be also used for the development of achromatic half-wave plate with subwavelength structures. Okay, so we made the model, the symmetric design, and the 5-layer achromatic half-wave plate. And for the AR part, I applied the fabricated shape on the sapphire. So this is the actual fabricated shape. And we can calculate the mirror matrix of this model using RCWA. And so I plotted only the transmittance and modulation efficiency and phase. So clearly we can achieve the high transmittance across the frequency band. And so, okay. This is one of the example of the performance of this model. So I took the average in the light bar flow frequency telescope. So from this result, we can achieve the transmittance more than 92% and modulation efficiency on 97% across all the band. So, and as a conclusion here is that, so even there's just complicated structures on the surface, we can calculate the optical performance of the achromatic half-wave plate. So, and this is the numerical calculation. So this can be useful for the future development. Okay, so from now, switching the gear, I'd like to introduce the recent development, the photo validation. We made 200 millimeter achromatic half-wave plate with sub-wavelength structures. So you can find such a structure on the white colored area. And so this is the 5-layered achromatic half-wave plate based on the anti-symmetric design. So that we measure the optical performance. So we loaded the sample and take the data and fit the data, and then calculate the transmittance and modulation efficiency and phase. So in the IP2, here is the component of the two-way signal of the modulated. You can find the two-way signal here. So the red line is the calculation, so the measurement is consistent with the calculation, and this measurement showed the high transmittance and modulation efficiency of the assembled sample. So this measurement is taken at the room temperature. So actually, since the property of the half-wave plate changes with respect to the temperature, so the measurement at the cryogenic temperature is also important. So for the validation at the cryogenic temperature, we made small achromatic half-wave plate with sub-wavelength structures. So the diameter is 50 millimeter. And so we cooled the sample and operated at around 20 Kelvin in the measurement. So we also rotated the sample by the rotational mechanism based on the superconducting magnetic bearing and with operating with the rotation frequency of 0.4 Hertz. So the same thing, we reconstructed the data, rotational data, and fit the data and calculate the modulation efficiency and phase. So actually, this includes the not only the optical performance, but also the systematic effect from the rotational mechanism. So this measurement has the important information to evaluate the rotational mechanism. And so if you look at the modulation efficiency and phase, the measurement is the consistent with the prediction. So from this result, our calculation methods is used for even the other cryogenic temperature. Okay, so this is the last page, maybe. So I'd like to introduce the other effect related to the half-wave plate itself. So the actual sapphire may have the imperfection of the optic axis. So it means the optic axis is not parallel to the sapphire surfaces. So we call it the off-axis side, and this misalignment of the optic axis had the out harmonics, the 1F and 3F, and so this the value increases with respect to the off-axis angle. So and this is can be the potential source of the systematic effect. So we need to model the off-axis effect. And so we should model that, but we have developed the analytical method to model the misalignment of half-wave plate. So, and this is the measurement of the misalignment half-wave plate with having the off-axis of 30 degrees, and the measurement is consistent with the calculation. So we can say that this method can be useful for the evaluation of the misalignment half-wave plate. So now that we presented the half-wave plate modeling, and its experimental validation. And so
you have 5 minutes, Ryota.
Okay. So, and show the analytical and numerical approach to calculate the optical performance of half-wave. So now we can propagate this result to simulate the delta R. So this is the current our progress. So we would like to move to the delta R simulation. So now, okay, this is a summary. So the modulation using the rotating half-wave plate is important to reduce the systematic effects. So, and for the modeling of half-wave plate, the analytical approach is very useful to design the optical axis of the half-wave plate. And with combining the structured anti-reflective structures, the RCW method can be useful to calculate the accurate performance. And in the validation, we fabricated the 50 millimeter to 200 millimeter achromatic half-wave plate with subwave structures, and the measurement shows the good agreement with the calculation and achieved a broadband modulation with the high transmittance. So in the future, we will propagate this result to simulate the tensor to scalar ratio, and evaluate the design and discuss if we need the improvement of the design. So, okay, that's all. So I'm happy if you have any questions and comments and suggestions.
Yeah, thank you very much. Thank you very much. Is there any question? Jon?
Yes, thanks for the talk. I guess it's a technical question, but this RCWA method for estimating essentially the Mueller matrix of this entire structure with the sub-wavelength anti-reflection coating. Have you compared the results of that analysis with sort of a naive approach, which treats the pyramids as sort of discretized steps in the index of refraction? So you would have essentially isotropic media, but just changing the density or changing the index. In other words, can we get away with using Tom Hillemann's code for calculating the Mueller matrix of the system?
So I'm not sure what is the naive the approach for the calculating the Mueller matrix of the subwave structures. But so then for example, we can compare the model of the pyramidal structures with the actual shape, and also we can compare the stepped based air coating with the actual shape, and also we can compare using the effective media theory with the RCWA, and we can find that the RCWA method can be more accurate than the effective media theory. In other words, the EMT is very rough calculation. There's the inconsistency in between the EMT and the measurement, so actual performance.
Okay, so I guess if you hold on this slide, what I'm essentially asking is if you replace those cones with 3 layers, which have an index of refraction going from 3 to 1 in succession, modeling the transition from, which is effectively what's happening here, transition from free space to the bulk material. Do you get the same answer, or does it actually matter that you're doing this more detailed analysis? Well, we can talk offline. That's really the question that I have.
Okay, any other question? So we are now a bit late, so maybe we'll thank Ryota again and pass to Fabio, which will talk about half-wave plate position reconstruction with Kalman filter.
Okay, do you see the screen?
Yeah.
Okay, full screen now.
Yeah.
Okay, perfect. So I'm Fabio Columbro from Sapienza University of Rome, and I'm involved in the development of polarization modulator units, in particular for two experiments, LSP Swipe and Lightbird. And so in this talk, I would like to present our approach in the half-wave plate position reconstruction, in particular with the using of a Kalman filter. So first of all, the angle reconstruction capability is one of the key points of the polarization modulator units. This is a very important point because an angle reconstruction error causes an E modes and B modes mixing. So this is related to the tensor to scalar ratio capability of our instruments. And so we can improve the angle reconstruction capability in mainly in two ways. The first one is an hardware improvement. And the second one is a software improvement. So by using the dynamical properties of our system to make a template and reduce the noise in the readout system to have more accurate reconstruction of the position angle of the half-wave plate during the rotation. So in this talk, I would like to present an overview of our drive system and our approach in the angle reconstruction. So I mean the standard approach, and then the results we obtained by adding a Kalman filter in our pipeline for the angle reconstruction. So first of all, the setup we used for the measurement, we developed a room temperature mock-up, which was very useful to develop the motor to spin the rotor and the half-wave plate, and also to develop the encoder and the readout system. So this mock-up has the same size of the Swipe polarization modulator unit, and this is the same from the point of view of the motor, and the readout system is the same of the one we will use in the cryo environment. And we do not expect any differences from this point of view from the angle reconstruction from room temperature test to the cryo environment test. Obviously, this mock-up is different from the point of view of the bearing because the superconduction does not work at room temperature. So we use the two low friction ball bearings here in the center instead of the superconductors. So moving to the drive system, the drive system is based on a feedback loop. So on the center of this loop, there is an Arduino board that is located here. This is the electronic box, and this is the Arduino board. So on this Arduino board, there is implemented a PID feedback control. And so the Arduino is able to control the frequency and the amplitude of the current which flowing in the coils. So these are the coils. We have 64 coils divided in 8 phases. And so we were able to control the amplitude and the frequency of the current. And if we modulate the current in each coil, we can push or pull the closest magnets, so small magnets located in the rotor, to spin the rotor itself. And during the rotation, we were able to read the position thanks to an optical encoder. So we have two encoders, an absolute one and a relative one that we will see later. And so, as I said, we can modulate the current in the coils and also the frequency of the current, and we can spin the rotor. While the rotor is spinning, we were able to read the position thanks to the encoder that is located here on the edge. And thanks to the encoder readout, we can give to the Arduino board feedback, position feedback, and so also a velocity feedback. And we implemented in the Arduino, so this is a software implementation, we have a PID controller. So the PID, this PID controller is mainly based on the proportional and the integrated contributions. We have also a derivative contribution, but this is mainly negligible in our system due to the high inertia of the system. We performed a tuning of the PID parameters, and after this tuning, we found a configuration which allowed us to have a very stable rotation of the rotor. But the question is, how much stable is this rotation? So, for example, we can compare the time of the optical encoder, of the relative encoder, with the expected time measured with the absolute encoder, and we expect to find, we would like to find a Gaussian distribution, and this is what we found. But going to in the details of what are the delta Ti and the delta T0. So, as I said, we have two encoders. So the first one is an absolute encoder. So we have a single slot on the edge of the rotator, and we read the time at the beginning of the slot. And so the delta T